screencast. Okay, what we'll talk about today is lists, tuples, and dictionaries, which are the most important of Python data structures. Lists, tuples, and dictionaries. By the way, if you use SageMathCloud right now, you'll find that there's a shared project with a worksheet in it that is exactly from today. And it looks like at least 9 people have it open right now. You're welcome to open it here. If you do so, then you can paste in things and so on. So I'll work with this worksheet, I think, during the class. See? All right, so let's get started. Let's see, also there's, well, I'll close that. Okay, so first I'll tell you about list comprehensions. So what I'm going to do is tell you about list comprehensions, which are a very clean, nice way of making lists in Python, which are much better than using, say, a bunch of for loops and appending to a list. And then I'll talk more about a whole bunch of really weird subtleties, which aren't weird at all once you understand what's going on, with how lists work in Python, and how they're in fact completely different than how they work in MATLAB and in R. And so it's really important to pay attention to what I'll talk about next after showing you list comprehensions. Otherwise, you might just hate Python and not get it at all. Okay, first, list comprehensions. So a list, I mean, I haven't really said much about lists, but here's a really simple example of a list. It has nothing in it, just a list of 0 things. See, and I made it by doing that. And if you have a list, you can append to it. So you could do something like v.append -3. And what that does is it changes the list so that it has the thing you just appended at the end of the list. In this case, there's just one thing there. And I could do it again and do v.append -2, and I get a list. And now that very same list has 2 elements in it. So with just that, you could do quite a bit with lists. A list is just a list of numbers. There's a couple of nice operations on lists. You can get the ith entry of a list. In Python, they're 0-based, like in most, pretty much all computer programming languages designed by computer science, software engineer type people. So v0 will give the 0th entry, -3, and v1 gives the 1th entry, -2 of this list. If you try to access an entry that isn't there, you'll get a big error message. And there's a couple of other standard things you can do with a list. If you do v.tab, you'll see most of them. So there's an append method, which I just showed you. And then there's count, which will count how many of a certain thing appears in the list. And then a couple of others. For any one of these, you can do, you can click on it and then do question mark and hit the tab key. And you'll see help describing how it works. Okay, dependent object to the end. There's one that I've seen people waste hours trying to find, which is how do you find how long a list is? How many elements are in it? It's not one of the methods. It's not like v.length or something like that. It's len of v, like that. And that gives you how many things are in the list at the moment when you call it. If I were to do v.append me, and then do len of v, what's the output going to be? The louder?
3.
Yeah, 3. It's definitely going to be 3. So let's do it. The reason it's 3, by the way, is it takes our list that has length 2 at this point in time, it appends me to the end of the list, and now the list is going to have 3 things. And so when I say len of v, it gives me back 3. Len just gives you the number of things in the list. Just watch out though, because v.length, nope. v.len, nope. In fact, there aren't any v.count. Nope, these don't work. They don't give you what you would want. Actually, I've never used v.count. I'm kind of curious what it does, given what I'm saying. Number of occurrences of a value. You can see that that's not going to give you how long the length of the list is. Though you might think based on the name that it would, but it won't. So I just want to point that out because I've seen so much frustration about this one little thing. And it's kind of a weird inconsistency in Python, in that most things in Python you call a method, but here you use a function and call it on. So just watch out for that one thing, okay? All right, now, let's say you want to make a list. One way you can make a list is by writing a for loop or a while loop or something and then repeatedly doing an append. However, there are other ways that are a little bit cleaner. And here's an example. What you can do is you can say, you say, make this, evaluate this expression where the variable, in this case n, goes over all the values in this range. So it's like the for loop, except all in one sort of compact thing. This looks like set builder notation, which you're all super familiar with as your mathematicians. It's very similar. So let's just change this a little bit and evaluate it. Instead of 5, I'll make it 50. Okay, so it's going to be really big. And it kind of scrolled off the side. Here you can see the expression is a little funny. It's n times 2, as n goes from 0 up to 9 inclusive, or range 10. If you wanted, say, the cubes of the numbers up to 20, we could do this. See? So this is a compact notation that's better than saying for n in range 20 colon v dot append n cubed, because you can do it all in one line. And just a little cleaner, it's easier to read, and it just feels like set builder notation math. Yes?
So you can do more, can you do like n cubed for n cubed in range, like you can be more complicated? Or does it have to be a simple n, like n following 4?
You can do really complicated stuff. So here's an example. The list of length 2, whose entries are x and y, where x is in the range up to 4, and y is in a list of 3 things consisting of capital X, Y, and Z. And you put a condition, namely that x has to be even. So you can have arbitrarily many for loops, and then you're looping over really the Cartesian product of the things in each of the ranges, or lists or whatever that you're looping over. And then you're restricting at the very end by an if. So you can take any collection of lists, or more generally iterable objects in Python at all. And then you can do for blah in one of them, for blah in the next one, for blah in the next one, etc. And what you're doing is you're iterating over the Cartesian product of those iteratable things. And then you're restricting at the very, very end, you put an if, and then optionally, you can put if and then some condition. And you'll only end up taking the things in that Cartesian product that satisfy that condition. And that's what you'll get the list of things. And so that you can avoid confusion when you're reading this, I'm going to show you how to turn this thing above into nested for loops. So what you'll do is v is the empty list. And then what you do is you just copy them in exactly the order they appear in the list comprehension into nested for loops. And in the very last case, in the very last for loop, if there's an if statement, you put it in. Notice I'm not typing anything, I'm just copying and pasting and putting colons at the end. And then inside of all that, you put v.append, and then you put whatever the expression is. Again, I'm copying and pasting. The only thing I actually wrote was this v.append and these colons at the ends of each line, and this initialization right here. Everything else I exactly copied and pasted directly from the list comprehension. You can always turn a list comprehension into a collection of nested for loops, as indicated right here, by just copying in exactly the order in which they occur. Okay? So that should help you in case you're confused about what order the things are iterated through up here, or what you can do. And just to convince you I'm not completely talking nonsense, I'll evaluate this, and let's see if it works. And gives the same thing. And indeed it does. These two are the same. Okay? Yes?
Are there ways to do the list comprehension things other than the append method? Or is that just what it does?
That's just what it does. So the answer is no. That's all a list comprehension does. A list comprehension is just like list builder notation. It makes a list of things in a nice compact way. It's really nice because one single line, which is hopefully pretty readable to you, is this, especially as a mathematician, is the same as this like big nested for loop thing. And it's kind of nice. It forces a certain amount of discipline because if you write code with all these nested for loops, well, it's kind of annoying because it gets all indented. And it's also annoying because you can slip in a little bit of code like between two of these and suddenly make the whole thing more complicated, maybe way more complicated and hard to understand. Like throw in some break statements, it can get really complicated. Whereas here you have a certain amount of discipline. You're just describing something by, you're kind of characterizing it. It's a list like this. So it results often in very readable code, which is good. You want code that's readable because you might have to read it later. Or in the context of this class, somebody's going to peer grade it, and you want them to be able to understand your code so that they give you a good grade. Okay, so just to summarize, this is the code I wrote above, but the key insight I want you to understand is just the order of the for loops and the if statement. It's all in exactly the same order as in the list comprehension. The list comprehension just takes like a for blah and blah, for blah and blah, for blah and blah, indented a whole bunch of times in if, and turns that into a single clean line. That is the same as iterating through the Cartesian product of those things and taking just the ones that satisfy a condition. Okay? All right, so exercise right now. And you can paste in a solution here if you want, or do it in your own project. Construct the following list using a list comprehension and the if-else exercise my sign that you wrote above. By above, I mean on Monday. So on Monday, remember we wrote a function that returned either negative, 0, or positive. So your goal is to make exactly the list that's right here by using a list comprehension.
Do we need to rewrite the mySign function?
You can copy and paste it and then reevaluate it. You'll have to open yours. I'll copy and paste it in here for convenience, since a lot of people have this opened already. And there's like 50 million copies of this sign, of my sign right here. I'll take who? Oh, it looks like my sign printed, but obviously you'll need to change it to return. Okay, who's Joshua Milhath? Right, there's I used your mySign function. Coincidentally, strange coincidence, I just turned all the prints into return. So Lalith, where's Lalith? All right, I'm going to try yours, right? Oh, you're doing it with, instead of a list oh, you did it with list comprehension. All right, cool. I'm going to try running yours and see what happens. Oh-ho. All right, so Lalith has completely solved this, but I'm going to walk around and make sure people are making some progress, and then in a few moments, see what happens. So, let me know if you're getting stuck with anything or what's happening. So you'll have to change the prints to return. Yeah, make sure to change the prints to return in the mySign function. And also, if you have any questions when I'm not here, just ask me. Sure, good one. Basically, here, this comprehension does have to call that function. Just where it has y, you just put mySign of x.
Is there something on?
Yep. I'm guessing that you maybe didn't reevaluate this. And so you changed it properly. It's naturally up. We're not sure.
I know actually I'm gonna do it with the.
So you want to put the folder, the function call is my sine of x. So x column my sine of x.
Oh.
So you want to, all you have to do is change this prints to return, and then reevaluate that, and then it'll totally work. Yeah, you don't even need, you won't need any of that other stuff. The stuff that's there, just delete it. Even, yep, boom, there, and then all the stuff delete. And then for, yep. And then close the script. That should be it. You have to define my sign. If you have my sign defined, that would do it. I think the should start at -3. What we thought is we end up with just filling up with far more things. Right. So I really want to do like I and then my side of I. It's like the second thing instead of J, it's you apply a function to I. Depending on it, and then the function will be that function on my side. Is that? I pasted it into the shared project so you can see this. Right there. Sure. That's it. So you're doing this in some magnified and produced shared project. So a lot of people are actually working on it. So that would cause confusion. You can open up your own project and work there if you want. So you have projects. Your project. Looks like there's like 4 people involved. Okay, good. Any questions? Yes. Okay, so all your code is right, but the problem is that you rewrote the code properly here, you didn't reevaluate this cell. So all you have to do is rerun that cell. And now the next one's going to work. Okay? Yeah, so it doesn't, if you change, like when you make changes, it doesn't instantly evaluate that. But the way I knew that you didn't run it was the blue line disappears. It's like an indicator that the cell is actually evaluated. You have a question?
So I was trying to ask earlier, she was like, you could print the first 20 cubes, right?
Yes.
For like, and then that range, do it. I was wondering, how would you do all the cubes from 0 to 20? Like, is there a way to like have the thing for expression as opposed to just like a single variable, like for n cubed in that range, or is that?
You could say, you could do sort of. You could make a statement at the end be if n cubed is less than 20.
Right,
so
but
like
then you have to
stupid
declare
things.
a range.
Yeah. So no, you can't. You can't just like, it's not like in math where you just can define a set by a logical condition and it magically figures out what that set is, which can be arbitrarily hard. So At least not in Python. I'm not using this. Yes. Oh, that's not That's totally okay. So several people are asking about the space. That doesn't matter. That completely doesn't matter at all. In the problem, I didn't put any spaces in, or they got removed somehow. But it's completely. You should have a space in the output. The space between the comma and in the output is completely irrelevant. Like in Python, 3 and a whole bunch of space 5 is the same as 3 in a single space. Maybe somebody's evaluating something right now. Okay, so it doesn't matter how much space you have there. Okay, any other questions? Yeah? So all you need to do is change the reference to return and then reevaluate that cell. So by the way, a frequent thing that people did was that they had the old version of this function from the previous day, and it has print rather than return. And so they dutifully changed them to return, but then they didn't reevaluate the cell. And hence, they were still running the old version of the function. So that did a whole bunch of people were bit by that. So whenever you make any change to a cell, unless you actually evaluate that cell, it doesn't in any way affect the Python process that's running. Okay, so keep that in mind. And this is fundamentally different than how something like Microsoft Excel works, where you change a formula somewhere, and then not only does that change like the state of something, it changes every output in the entire, potentially every output in the entire spreadsheet. It's very different here.
So
yes.
About like when we're working with V, like the list V, like you kind of just had a bunch of different cells modifying it.
Yes, that's right.
So is it like there's a working list of like variables, like
Yep.
the Sage worksheet?
Yep. Yeah, and there's a command, I think, show identifiers that will list them, or at least list the, is it show identifiers? I don't know. It might be show identifiers. I tabbed on it. Okay. It keeps tab completing because I. Okay, so yeah. So these are things that were defined in this session. And if I define something else like e equals 10, and then I do show identifiers, then in addition to whatever's listed there, there should be v now. Unless, of course, the whole thing got restarted. Well, let me make it very distinctive. That. I think I'm going to switch back to my own private worksheet so that, because people could be running stuff and just kind of a lot going on. So this is back in my own private project. But, come on, what the heck? Open. Why is it opening? Well, that's not good for me. Just so it's loading. But anyways, Sage worksheets, the way to, there's really like a Python process just running there. And also if you do things like %r, then there'll be an R process that's also running there. And it seems really slow suddenly. So let's suggest some. System load is very low. Oh, okay, there it is. All right, so I'll do the same thing I was just doing. So set a variable and then do show identifiers, and that'll get listed as one of them. Way slower than it should be. Okay, so if we look, there should be. Oh, these aren't even sorted. Well, here it is. Here's the identifier that got added. And then if you were to restart the session, that identifier would get wiped out. So, okay. All right, so any, I want to look at the shared worksheet. Oh. Database is suddenly slow. Okay, well, I'll move on. So I'm going to tell you about the subtleties involving Python lists. So Python lists are very subtle due to the basically the semantics of Python, where assignment is not copy by value. Assignment involves just getting another reference to an existing object. So I'll show you a bunch of examples to illustrate what I mean by that and how it makes Python lists very subtle. And then I'll show you the how things work in a bunch of other languages, including MATLAB and R, and how they're different than what you have in Python. And so if you're used to those languages, you'll be potentially very confused. So first, let's look at this one example and see what happens. So I'm going to let A be the list consisting of 1, 2, and 3. And then I set B equal to A. And what happens in this line 113, is very different in Python to what happens in many other languages. Basically, if you take all the languages to define list of the languages that were created by software engineers, one thing happens. And if you look at most of the languages created by mathematicians, a different thing happens. And Python was created by software engineers. So when you do B equals A, something happens. And now when I do B square bracket 0 equals 5, what that does is it replaces whatever the first entry of the list B is with 5. And now let's print out A and B. Okay? So what you get, again, in Python you get one thing. If you do exactly the same thing in a different language, you may very well get a different answer. Or if things are really slow, get nothing. This is slow. Okay, now it's working. So notice that A and B are identical. So both A and B have their beginning entry changed to 5. And the reason is because when you set B equal to A in Python, it just makes the variable B another reference to exactly the same list that A is a reference to. Under the hood, there's some object in memory, and there's a command, I think, ID, which will give you the memory location of that object. Whoops, oh, I restarted a whole bunch of times, so it got unhappy. Okay, so if I do ID of A, it gives me the memory location of what A points to. If I do ID of B, it gives me the memory location of what B points to. And in this case, they're the same. Okay, so now let's look at what happens in MATLAB. Octave is a free open source clone of MATLAB. And if you do %octave in a Sage worksheet, or type octave on the command line, or switch a Jupyter notebook into octave mode, you get something which is very similar to MATLAB. You can use almost exactly the same code. So I'll let A be the array in MATLAB, 1, 2, 3, set B equal to A. In MATLAB, things are 1-based, so B parentheses 1, that means change this entry right here. So I'll set A equal to 5, and then I'll print both A and B. And then we'll see what happens. And so when I did that, by the way, it starts up a copy of Octave running, and then any further interaction goes back and forth to that copy of Octave. And look what happened. A and B are different. A is 1, 2, 3 still, and B is 5, 2, 3. So when you do B equals A in Octave, it creates a whole new object, B, which is like a complete copy of A. Okay, so that's completely different. And when you make changes to B, that doesn't in any way touch A. Okay, let's see what happens with R. In R, what happens, I'm setting A and B equal to this vector 1, 2, 3, and then I set B square brackets 1. Again, in R, it's 1-base, not 0-base, to 5, and then I print out A and B. And notice they're different again. So in R, just like in MATLAB, when you do B equals A, it makes a complete copy. At least conceptually in your head, you should think of it as making a complete copy of A. Under the hood in the actual implementation of MATLAB or R, they could, of course, not actually make the copy until you make this change, as in efficiency optimization. But as far as how you should think about how it works, it's like it's made a complete copy. And just a few more examples. Here's JavaScript. In JavaScript, A is 1, 2, 3, B equals A, B square bracket 0 equals 5, and now let's print out what happens. And notice that they're the same. So this is just like what happens in Python. It's 0-based indexing, and it's copy by reference. Python and JavaScript are identical in that regard. Okay, and to throw yet another one in, there's a language called Julia, which is fairly new and came out of MIT and is trying to compete with MATLAB. And let's see what it does. So it'll do A equals 1, 2, 3. Julia, by the way, tries to look somewhat like Python and be kind of easy to write like Python, but it's compiled, and so it's supposed to be very fast. In any case, let's set A to be 1, 2, 3, B to be A, and then do. So Julia uses square brackets like in JavaScript and Python, but not like MATLAB. And it's 1-based like in R and MATLAB, but not like JavaScript and Python. And so you do B square brackets 1 equals 5, and look what happens. And notice it's copy by reference now. So you've actually changed both of the arrays or lists. The point is that the semantics of what happens when you run this little piece of code, every step almost is completely arbitrary what the choice is. And you can look at a whole bunch of top programming languages, and every choice has been made differently. Okay? So just relax a little. That means there's no right answer, and that for certain things, maybe one answer is good, and for others, the other one's good. You'll see this, though, throughout programming languages. Every possible case where there's some potential ambiguity, you can almost find a programming language that's made both of the choices. Like one language will have made one choice, and another language has made another choice. This is incredibly frustrating if you try to program, because you frequently have to write little tiny test programs to see what the language actually does. You can't just reason from first principles like you do in mathematics. You have to look it up in the documentation or write little test programs for everything, because there's just no right answers. There's just a huge number of ridiculous arbitrary choices. Yes?
So if you had set B equal to 1, 2, 3, would it have made a whole new object regardless of the programming language you were using?
In all cases that we're talking about, yes.
Okay.
But I wouldn't depend on that in general for any programming language ever. You could imagine, so you could imagine a language that goes through and sort of folds the constants all into one for efficiency reasons, maybe before doing something else, and then it wouldn't. And I can think of situations where that might be a reasonable thing to do, especially if 1, 2, 3 is often very large. You could easily imagine a pre-parsing step that takes all the constants and factors them out and then sets things equal to them. But yeah, I think in these languages, I'm pretty sure. Honestly, I'm not 100% confident. I haven't tried that in Julia, but I'd be shocked if that wasn't the case there. So basically, let's see. Okay. Somebody's using my CPU. Yes. No? Well, it's easy enough to test that. Okay, so let me just show you some of the really subtle consequences of this in Python. Jeez, what is going on? Okay, so right now it's working fine. Okay, so look at this. Set V to be the list 1, 2, 3. Set W to be the list whose entries are V, V, and the list 1, 2, 3. Okay? Now let's print this out. So I was printing out the version from before. Things are all messed up. Okay, so notice what it looks like when it prints out the result. It just looks like 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? So it's just the list whose 3 entries are the list 1, 2, 3, 1, 2, 3, 1, 2, 3. But I want to emphasize that looking at this output doesn't actually tell you what you're looking at. Okay? Because watch, if I take the first list here, that's what W square bracket 0 gives me, and then I change its first entry, or 0th I should say, to Sage, look at the result. Now what is W equal to after I do that? What do you think? How many Sages am I going to see when I print it out? 2. So you print it out and you see Sage twice. And the reason's because W, which looks like this, it has 2 copies of the same list and then a third completely different list. And when you change that first list up here, first entry to Sage, you're changing these 2 simultaneously, but not the third one. That's why I did this. But you can't see that by just looking at the output. And so it's kind of a subtlety. So I guess my little tiny moral is don't judge an object by its cover, namely by how it prints out. There might be something subtle going on there. And you can imagine how if you didn't know about this sort of behavior, you could hit some bugs that are very hard to debug, and you could get very, very confused. Fortunately, at least as I pointed out before, let's say you want to see the memory locations of all the objects in that W points to. You could just say ID of X for X and W. That gives you the memory locations of the entries in the list W. And you can see the 2 of them are the same and the third one's different. So you can really get your hands on what's going on. Okay, there's a module called copy, and it has 2 functions. So when I said import copy, this is how you import some code from a Python module. And Python has an enormous standard library. There's a link up there to the Python standard library. And by doing import copy, I then get access to a bunch of functions in that module. And if I run this code, then I can do copy.tab, and I'll see that these are the functions in that module. There's copy, there's deep copy, and then there's some other stuff. Weak graph, etc. So look what happens when I do copy. So the copy function, it makes a copy of a list. So what happens is W and W1, they're different lists of 3 things, but the 3 things that W and W1 point to are both the 3 original objects, namely this list twice and then this new list. And so if you change an entry inside of W1, then that changes it also in W. And that's why these are both being changed. On the other hand, if you appended something to W1, that wouldn't change W, because they're not the exact same object. Okay? Yes?
You call the copy.deep copy of W.
Then you get then it will descend the tree and make complete copies. Basically, it goes through each object, and then it looks inside of that object, and so on, as far as it has to. Sorry, and then tries to copy the entire object over. And that gives you a genuine deep copy with semantics similar to what you have in MATLAB.
Is that something like impossible in Java? Like, can you get at the fields of an object and then say, like, you know what I'm saying? Can you iterate over the fields of an object?
I don't think you can at runtime. That's one of the things that's different about Python from compiled languages, that you can do all kinds of subtle stuff inspecting an object at runtime. And this is all happening at runtime. It's dramatic. Like, interpreted languages like Python enable all kinds of subtle operations at runtime, which you just can't do in compiled languages. We're interacting with a running program here, with some running state, back and forth. So it's just a very, very different experience. That's why, like, Python is slow. In many cases, you can write a Python program, and if you aren't calling out to libraries that optimize code, it can be somewhat slower. And you might wonder, why doesn't somebody just write a compiler for Python that makes it super fast in all cases? And the reason is partly that the things that you can actually do in Python just can't be mapped to things that you would do that can be compiled, because you're doing all kinds of looking at the state of objects at runtime and inspecting them. And in order to enable that, there's a lot of data structures involved that are sort of difficult to analyze at compile time. So here, when I do deep copy, I just have a completely separate copy. So really, this one line is very similar to what happens with R or Octave or MATLAB. But somehow the name and being explicit about copy.deep copy suggests that this might be inefficient. Whereas in R or MATLAB, you'll just naturally write something like this, because it's your only option, and you'll end up writing code that's inefficient as a result. So somehow Python gives you both options. You can either do copy by value, which is what copy.deep copy provides you, or copy by reference. Whereas when you're using, say, R or MATLAB, you have only the option of copy by value. So it's sort of somehow the mathematical languages like R and MATLAB, they limit your options somewhat naturally in a way that may not be so efficient or powerful, but on the other hand, it's less likely that you'll write maybe buggy code, or that debugging will be really confusing. On the other hand, Python is very powerful. Okay, so there are a couple of other data structures I want to give you a glimpse into, namely tuples and dictionaries. I won't mention sets today. Tuples are almost exactly like lists. The only difference between a tuple and a list is that you can't delete entries from a tuple and you can't append things to the end of a tuple. But otherwise, a tuple is just a ordered list of references to Python objects. That's all it is. And so here's an example of a tuple and a list.
And you can modify the entries of a tuple?
If the entries of the tuple are modifiable, then you can modify them.
Right, I mean,
But you can't
can change the
reassign.
swap references?
No, you can't change what's referenced. So a
tuple,
tuple, it's like, in this case, it's 3 references to Python objects, and you can't change what Python objects are being referenced. However, if those Python objects have some way of changing their sort of internal value, you can't stop that from happening. So tuples aren't completely unchangeable, but you can't change which objects are being referenced in this. So they're very, very similar to lists, but where you're not allowed to make a lot of changes. So here I can change v1, but if I try to do t1 equals 3, this should give an error. This is not allowed. Well, yeah. So this should give an error. Boom, there's an error. Tuple object does not support item assignment. So tuples they kind of support a subset of what you can do with lists. And you might think, what's the point of tuples at all if that's what they do? Well, if you make a tuple with a couple of things that can't be changed inside of it, for example, if I make this tuple 1, 2, 7, then there's really no way to change, because you can't change 1, 2, and 7 themselves. You can't change this tuple. And so it's actually really useful to have something that you can't, even though you make a copy of it by reference and you send it to some other function and that function uses it, there's no way that this 1, 2, 7 is ever going to get changed. So that's really, really handy. And I'll show you in a moment when we look at dictionaries how useful that is. So I'll skip this and this because we're almost out of time. Okay, and now dictionaries. So another important data structure in Python is called a dictionary. This is also called associative arrays, often in computer science. And in mathematics, it's really what we call a function. It's just a function from some finite set to another finite set. It's, at one point in time, you can change them and then it becomes a different function. So this is the notation for just writing down a dictionary. You put a brace and then something, anything that, well, I'll tell you what you can put in the domain, but anything that can't be changed, colon, and then what it maps to. So in this case, 525, 10, 100, and 38. So then you can evaluate this, and then it prints out just the way it looks. And what you can do is to call it, you do d square brackets some number, at least or whatever the keys are. You give it a valid key, and then it'll give you back whatever is to the right of the colon. And there you are. So I'll continue talking about dictionaries on Friday.